question 26, and this whole question, this is from 2014 HSC. Question 26, quite a difficult question, the second part to answer. The first part is all, basically the whole question's about using the equation E equals HF, and that's energy equals Planck's constant, H, 6.6, just trying to remember what it is, 6.626 times 10 to the minus 34, and frequency is the frequency of light required, given to a photon. So this is the energy of the photon, frequency given to the photon, and Planck's constant. In graphs where you have kinetic energy and frequency, that's the slope of that line is Planck's constant, so it's H equals kinetic energy, rise over run. And you can get that from rearranging this equation. H equals E divided by F. E divided by F. So this question's relying on looking at this equation, and we're told in the question here that the voltage set was 4.1 volts when the experiment was done the first time. If we go to the next page, the actual part B question, so this is information that we're going to use. It's an aluminium surface, so it's going to have the same surface in here. When light hits that surface, photoelectrons are released, they go to the collector, they go round, and they complete the circuit. They're going to do the experiment again, and we'll look on the next part of the get the voltage. 4.1 experiment. So they want us to do some graphing. They've done one line, and this line here is for 4. I'll just go back to volts. Now they want to do the experiment with a reduced voltage of 0 volts. Now the problem that we have, this graph shows electron volts. Now 1 electron volt equals a volt times the charge of an electron. So it's 1.602 times 10 to the minus 19 joules. It's the energy lost by an electron as it passes a potential difference of 1 volt. So if you see this electron volt around, so in the case of ours, 4.1 volts equals 4.1 times the charge of an electron. And it gives you the energy of a volt. So here we've got 4.1 electron volts now. It should be electron volts. And this side, oops, sorry. This here, now we've got the equivalent in joules. So whenever you see electron volt, to get it to joules, you times by the energy of an electron, or the joules of an electron, and it's the same as the charge of an electron. Okay, we're reducing it, so the intercept for our graph is going to go down minus 4.1 electron volts. So if we look at this, we want minus 4.1 because it's going to go down from 4.1, which it was done first, down to 0 volts, so it's going down. And the charge on this electron, we're going to put that as minus. So if we do this calculation here, we'll get 4.1 times minus 1.602 times 10 to the minus 19, and it equals 6.56 times 10 to the minus 19 joules. That's the energy, and that's the energy that's going to be down here on our graph. So no longer at 0, we're going down. That's the voltage produced. This is in electron volts, so we had to convert it to electron volts. Now this amount here, we can then use that. That's our E for our new experiment. But we want the frequency, so we can figure out whereabouts on this graph we're going to have an intercept for that frequency. In this bottom scale here, this will be the y-intercept. And we want the frequency so we can see what the x-intercept on that graph is. So we can do that now. We want, that's E, so E equals HF. Now we rearrange that. We want frequency, so F equals E on H. Now we have our energy there. And the H value, it's on the data sheet, but on the constants sheet. So our frequency, if we look here, works out to be 9.9 times 10 to the 14 hertz. Now, if we go up to the graph now and have a look at that, and I'll just delete a few of the lines here, get them out of the way. So if we look at 9.9, we've got a point here on our graph. Now we need to draw a line that is parallel to this other line. That's the line for aluminium. No matter what the voltage is, so when you change the voltage, you're just increasing the amount of energy the electrons have. So this line would just move. If you had more voltage, less voltage. Okay, we need enough less voltage to go through that point and go down to our minus 4.1 intercept. Let's just clean up this. Okay, we change to red. So 9.9 times 10 to the 14 hertz is there, and the line must be parallel to that other line that we have on the graph there. So it's going to go, and you could use a ruler to check that this is parallel. Okay, and I would use a ruler definitely. I don't have a ruler at the moment, so now once we have that, we can then do some calculations. In the question it says 1.2 EVs. So we have our new line, we go up to 1.2, about there, we go across, and then down. And we get an answer of about 12.8, and it's times 10 to the 14. So that's our answer. Now the hardest part for this question is trying to work out what an electron volt is in joules, because we want E equals HF, we want energy. So just remember, when you see electron volt, you can convert to joules by multiplying by 1.6 times 10 to the minus 19. And that's the charge, or the energy lost by an electron as it moves through 1 volt. A difficult question, and that's the frequency we wanted. That frequency will give us a maximum of 1.2 electron volts. So a difficult question, but to get marks, and I'll just show you some of the ways to get marks that the Board of Studies used. This is from the Board of Studies website, the marking guidelines for question 26b in 2014. You can see if you got stuck in the exam and you weren't sure how to go about answering this question, The question itself is about E equals HF, alright? And if you rearrange that, we get F equals E on H. If we look here, to get 1 mark, you need to show a correct feature on the graph. Well, we know that if this graph was produced using 4.1 volts, there's going to be a lower voltage. It's going to produce lower energy, maximum kinetic energy. So we knew the graph would be lower. So you might want to have an estimate of where it would be. The value of frequency, you'd be using this formula to try and figure it out. You need to have this line parallel to this line to get part of those marks. So that would get you part way there to the marks. As you can see here, it draws a line on the graph. Now the intercept is the hard part. And to get that, to get these higher marks, you needed to know that an electron volt equals the voltage times 1.602 times 10 to the minus 19 joules. The energy of the voltage of 1 electron. Okay, so it's a very small amount. Normally a volt is a joules for a coulomb of charge. We're using just the charge on 1 electron. So we multiply the voltage we're given, 4.1 times 1.62 times 10 to the minus 19. And that'll give us a value for energy in electron volts. And that's what we needed. The frequency that we wanted the intercept for, which turned out to be 9.9. And you can see the calculation there that the Board of Studies has supplied. So they've worked out here this volts in joules of energy for electron volts. Then they've used HF equals that, so E equals HF. They've rearranged it to get frequency. And there's Planck's constant, H, and here's the energy for 4.1 electron volts. Now, if we go from 4.1 down to 0 for your experiment, then it's going to make a graph that's down further, minus 4.1. So that's what they're relying on, and the intercept will be 9.9, which you can work out. Very difficult question, but I hope that helps a little bit. Sort of question you might get part way there with the marks, and if you get time, come back and have a go at really trying to crack that question. I wouldn't stick on that question for a long time. Try and estimate that graph first. We know that for aluminium, changing the voltage should just change, but the slope will stay parallel. So you would have got some of those marks.